This is the experimental method shown on page 167 to find out the approximate focal length of a lens. We have two diode lasers here, and we have a lens positioned at a distance from the diode laser such that both the the beams are shown on the lens and they are caught on a screen. We can actually observe that these two spots are separated. So if we now start moving this one as we come closer and closer, you can see that they will merge into one single spot. At this time, if you measure the distance between these two, this itself is the approximate focal length. This is a very simple way of showing how to measure the focal length, but there's even a simpler method than this, because you don't need to use two diode lasers. All you have to do is take a distant object and then form an image on a wall or with a screen and make the image sharp to the distance between the image and the lens gives you the focal length. Well, if you have this setup with the diode lasers, the lens, and the screen, this is the easy way of showing it. If you don't have this one, all that is needed is the lens, a window, and a wall. That's all you need, and you can focus the entire thing onto the wall. Now we are ready to show the experimental setup for the measurement of focal length of the lens. We use an optical bench. This is called an optical bench. This has got a number of divisions, centimeters and millimeters marked on it. And these uprights, you can loosen them and you can actually put them wherever you feel like. So you can move this one forward and backward and you can put them anywhere. This is a lens holder where it can hold the lens. This is our object. It's got a lamp inside and you can see there are two arrows. So this will be our object, and when you measure the position of the object, you don't measure from the center of the lamp, but if you put it down, you measure it from here. So once you put it at somewhere, you don't have to move this one. So this will be our object position, and the distance between this and the lens, this is the object distance, and from the lens to the screen, this is the image distance. Since we already have the approximate focal length, so we start the experiment by putting this lens at a distance slightly larger than the focal length, because we know that if we put this lens at a distance less than the focal length, you cannot get an image. It will be a virtual image. So therefore, what we will do is we'll put this one slightly greater than the focal length. Then we can move the screen back and forth until we get a nice image. Well, actually, you need to go much farther. So what we will do is we'll move this one a little bit closer, so you can easily, nicely see the image. This is a image beyond 2f, and this is an inverted image. You see the arrow is upwards, the arrow is downwards here. See? So we can not only catch the image, but we can describe the image also. For instance, I will describe this one. In this case, the image is a real image. It's an inverted image at a distance more than twice the f, right? And what we can do is we can move this one further up like this, so that this time it is more closer to the twice the focal length. Therefore, the picture will become smaller. See this? This becomes smaller, but still inverted, still real. Because when we say real, it means we should be able to capture it on the screen. And we can further go down this way, still more like this, and then we can focus this sharply. So this shows, you can see it's a very, very small image. So this time it's a real image, inverted, but between f and 2f. This distance is larger, this distance is smaller. So if you call this one as P and this one as Q, you can easily show 1 over f equals to 1 over P plus 1 over Q. and you can calculate the focal length. That's what we are going to fill up in our table.